Notes are going to cover a little bit about operations with functions and then some applications with inverse functions. Um, so we've touched on this a little bit before. When you perform operations on an entire function, you can write it with this notation. So f plus g of x simply means you're going to add the two functions f of x and g of x. And then similarly with these other operations, it just means we're applying the operation to the entire function. So here I'm going to find f plus g, f minus g, f times g, and f divided by g for these two functions, f of x and g of x. So f plus g of x is f of x plus g of x, which just means I need to add and combine like terms. X squared plus 3x minus 4, and then plus 3x minus 2 would give me x squared plus 6x minus 6. So f minus g, same idea, but we do have to be careful with our parentheses. So I'm still going to have x squared plus 3x minus 4. But when I subtract the entire function g of x, I have to be careful and make sure that I distribute this negative appropriately. So that's going to give us x squared plus 3x minus 4, and then minus 3x plus 2, which then simplifies to x squared. 3x minus 3x goes to 0, and then negative 4 plus 2 becomes negative 2. F times g of x is f of x times g of x, which would be x squared plus 3x minus 4 times 3x minus 2. And we have to multiply these with the distributive property. So x squared times 3x would be 3x cubed, and then x squared times negative 2 gives us negative 2x squared. 3x times 3x gives us 9x squared, and 3x times negative 2 gives us minus 6x. Negative 4 times 3x gives us a minus 12x. And then negative 4 times negative 2 gives us a plus 8. And then when we combine all the like terms, we get 3x cubed plus 7x squared minus 18x plus 8. Which this would still be technically correct if I left it here, but it did specify to multiply the two functions out, so it never hurts to expand it. And then f divided by g of x we're just going to write f of x as the numerator, x squared plus 3x minus 4, and g of x as the denominator. And that's as much as we can simplify f divided by g of x. So composition of functions is a new concept. So we have, suppose f and g are functions where the range of g is a subset, and that just means the range of g contains the domain of f. Then the composition is denoted like this open, that's an open circle, f of g of x. And what we do is we're going to find g of x and then input that as the new input to f of x. So we say f of g of x. So g of x becomes the input g of x becomes input for f of x. And what that looks like is over here. So we have f composed g of 1, or f of g of 1. So f of g of 1. So I just need to find g of 1. And I know that g of 1, based on this, g of 1 is 3. So really this is f of 3. And then f of 3 is, right here, 3. Notice g of f of 1, you might think it's the same, but it's really not, because this says first we're going to find f of 1. And f of 1 is equal to 2. So this is now g of 2. And then g of 2 is 2, based on this. So a word we could use here is that composition of functions is not commutative. The order does matter when you compose functions. So now we're given that g of x is 3x minus 4 and h of x is x squared minus 1. And we want to compose g, or we want to find g of h of x. So to find g of x means, like g of x means I'm inputting x for the variable in g. So g of h of x means I'm going to input h of x for the variable in g. So g is 3x minus 4, but instead of writing 3x minus 4, so we have g of h of x would equal, so g of x is 3x minus 4, but I don't want g of x, I want g of h of x. And h of x is x squared minus 1. And then g of x was 3 times something minus 4. So this part was h of x. And I inputted that for the variable in g. And then I could expand and get, if I distribute the 3, I would get 3x squared minus 3 minus 4, or 3x squared minus 7. And then h of g of x, I'm going to do the same thing, but I'm going to switch the order. So first I'm going to start by writing h of x. So h of x was, so h of g of x. So notice h of x is something squared minus 1. Here my something that's going to be squared is 3x minus 4. And then I'm going to subtract 1 from that. So this part that's being squared is g of x. And then if I expanded that to simplify it, I would get 3x minus 4 times 3x minus 4 minus 1, which would give us 9x squared minus 12x minus another 12x, so minus 24x plus 16 minus 1, which would be 9x squared minus 24x plus 15. So notice again that g of h of x and h of g of x are not necessarily the same thing. So the other thing we talked about in class today was inverse functions. Inverse functions we talked about in class are if one of them contains a, b, some arbitrary point, then the other relation contains b, a. So these are flipped. There's no sign change. There's no a lot of people, when they write inverses, they want to like flip fractions and whatnot. But all we do is switch x and y. So we're just going to switch x and y. So if f and this is the sign for f inverse, f to the negative 1, are inverse functions, then f of a is equal to b if and only if f inverse of b is equal to a. So, and here we're not going to do the graphing part. But a quick way that always works to find the inverse, well, not always works, but works for anything in this class, to find the inverse of any function. So say we had y equals 2/5 x minus 1/5. Then, so notice to find the inverse, we just switch x and y. That's that's what's always in the new function. So 2/5 x minus 1/5. Then to solve for the inverse, all I have to do is switch x and y. So I'm going to write x equals 2/5 y minus 1/5, and then solve for y again. So to do that, I would add 1/5 to both sides. So x plus 1/5 equals 2/5 y. And then multiply both sides by the opposite, or the inverse of 2/5. So I'm going to multiply both sides by 5/2. So that would give me that y is equal to 5/2 x, and then 5/2 times 1/5 would be 1/2. 5/2 x plus 1/2. And the way it's written on the left side of the equation here, so the way it's written here, it's kind of how we were finding them in class, right? We said if the original equation was multiply by 2/5, then subtract 1/5, the inverse would have to be first add 1/5, then multiply by 5/2, the opposite of 2/5. The only thing that's different here is we distributed the 5/2. So a more complex example is if we have f of x is 2 times x minus 2 squared plus 4. So we're just going to swap x and y again. So x equals 2 times y minus 2 squared plus 4. And then I'm going to solve for y again. So I would subtract 4. X minus 4 is 2 times y minus 2 squared. Then I would divide by 2. And then I would take the square root of both sides. And because this is squared and we're introducing a square root to an equation, we have to do a plus or minus square root. So both sides of the square root are the inverse of the function. So plus or minus square root of x minus 4 equals y minus 2. And then we would add 2. So y is equal to plus or minus square root of x minus 4 over 2 plus 2. Notice that this is not a function. So we said in class the inverse of a function is not always a function. However, if we were to restrict it and only take the positive square root or the negative square root, then it would be a function. It would be a square root function. All right, so next class we're going to explore a little bit more about inverses and how they connect to composition of functions.